Good evening. So I'll be talking about machine learning, artificial intelligence, so similar allied areas. And I'll be talking about some of the work which Mayank does, Shanmuga does, Krishna does, Anirban does, and I do. And I'll be starting off with more applications, and gradually I'll discuss some of the more theoretical aspects also done in the group. So for example, let's look at some of the work which Mayank does. So let's see if I Google my own name, right? So I see this thing which is known as a knowledge panel, right? So effectively, if you see what companies like Google and all are trying to do is to organize the information. That's also what they say is their motto or their goal, is to organize the information to make it more accessible, to make it more useful, to make search easier. And they're trying to make search available on various kinds of data. Like this is, for example, mostly text data, but you already see a lot of information here. So Google probably knows that Nipun Batra is a researcher, and therefore the affiliation, the research interests are important. What is probably not important is, let's say, the kind of music I might have created, because in this case I'm represented as a researcher. So therefore my Google Scholar profile, my publications are important. But let's say if you had to look at Amitabh Bachchan, right? So they're available on Ghana, YouTube, Spotify makes sense. The Wikipedia linking makes sense. The upcoming movies make sense, movies, TV shows, the popular songs, and also what people search for, right? So think of this as what companies like Google have enabled is to create this nice collection of data and have sort of organized in a way which makes it more useful to the end consumer, right? Now, let's take this whole discussion to the context of research papers, right? So all of us are now looking at the deluge of papers which are coming in various conferences, journals, on things like archive. There's just so many papers that no one can keep up with them, right? So Mayank and his team have built this tool called NLP Explorer, right? So I don't know the full demo, but let's see that if we were to search for some papers in the domain of NLP. So what we're trying to do is to organize now this literature. Again, there are tens and thousands of papers. How do I organize them in a way which is, let's say, hierarchical in nature? Which two papers are similar to each other? Which set of authors are connected to each other? Are some authors discussing some topics? Which topics get more prominence at what point of time, right? So you're able to understand a lot of trends this way, and you've organized the information so that tomorrow, if you're trying to build up a related work, you're trying to understand some concepts. For example, here I'm trying to understand LDA, latent digital allocation. So I see a few papers, I see some the authors in some alphabetical order. And let's pick up, let's say, this first paper, right? So beyond what you might have already seen in Google Scholar, you're also seeing a bunch of other things, the kinds of URLs being referenced in the papers, the field of study, right? So now you're not only getting the paper, but how do you broadly categorize this paper? You also see, interestingly, that they have made a data set available. They have made the languages both English and other languages. They're working on name entity recognition. And interestingly, you can also get a sense of similar papers. So you can, in fact, start off with one paper, you can go to the other papers, right? So this just makes the whole searching for academic papers, looking at the different context, a lot more interesting, right? And let's look at another different aspect of the same. Let's look at another tool called NLP. So now a lot of the discussion about, so we're talking about organizing information, right? A lot of the information about various academic articles or about various events now happens on the social media, right? So a lot of these things may or may not come in, let's say, a Wikipedia page or in the conference proceedings, but these things are important. For example, what are the papers which are getting a lot of attention on social media, on Twitter? Which of them are getting liked a lot? Which of them are getting retweeted a lot? Which of them have a lot of ambiguity, or which of them have a lot of controversial opinion discussions, right? So all of these things is yet a different aspect of organizing the information. And this is, so both of these things, while they may appear simple, but they're very challenging because you're dealing with natural language, right? So natural language in the written sense, not in the spoken sense. But think of the papers, right? So academic papers are written in slightly different forms as to what you may be speaking with your colleagues, right? They may have tables, they may have figures. How do you make sense of all of them? and the discussions about on them on Twitter. Some of them may be English, some of them may be Hindi, some of them may be multiple languages, some of them may have spelling mistakes, right? So how do you still organize all of that information? Some of them may, in fact, have some notion of you're trying to estimate the sentiment around some papers, right? So all of these are important challenges in this domain. And another thing I'd suggest all of our colleagues who are watching all of the students, all the colleagues who are watching this video is to maybe just go to the websites of each of the faculty and see. So maybe there's a linking error, but let's see. So let's look at the Google Scholar link for Mayank, and let's see some recent papers. And so, for example, we're talking about code mixed natural language processing, right? So for example, in the context of India, many of us are talking in English, Hindi plus English, or some other languages, right? Natural language systems will break because they're built only for some specific languages. So how do you get them to work, right? So another interesting paper is this, let's say, Tablex. So this is benchmark dataset for structure, content, information extraction from scientific tables. So you have papers. So all of the papers which are doing some empirical comparisons, empirical evaluation, they'll have some tables. So just looking at the tables, can I tell which paper is good, which paper is better than the other? Probably not very easy, even for a human being. But again, let's go back to the goal, which I said earlier, of organizing the data in a more useful fashion. So how do you create systems which can extract this data from these tables, which are generally LaTeX tables? Can you extract the data from them, create a leaderboard kind of a system, which paper is doing better than the other based on the table you're seeing, right? So these are very interesting, very challenging, very open kind of projects. And another interesting project which Mayank and his group are dealing with is trying to organize literature around Mahatma Gandhi. Right? So again, some of this is available in books, some of them is available in different languages, some of them is available in books which are not easily accessible. So there are various interesting challenges around this. Let's now talk about some of the work which Shanmuga does. So Shanmuga works in computer vision, right? Sorry, is there any question? Does anyone want to ask anything? Or is there a question? Or does someone need to be unmuted?
I think, yeah, that's probably an accidental unmute. Yeah.
I see. Right. So when we're talking about computer vision, so all of us are now carrying the most powerful cameras which have existed in the past century, right? Our smartphones. Now, should we buy a Pixel? Should we buy an iPhone? Should we buy a Samsung phone? Should we buy some Xiaomi phone? How do we decide? Many of the times we decided based on the camera systems, right? But if you see, Pixel phones have one camera, whereas phones like iPhones have, some of the iPhones have two cameras. Some of the Samsung phones have three cameras. I'm talking about the rear cameras. And then some of the Xiaomi phones may have four cameras, right? So which of them works well, right? So again, it's a very subjective question. So a lot of this is based on, the decisions are based on how these different companies approach what is known as computational photography. So taken a raw image, which is just a signal, how do you compute what you want to show the user, right? How much of that is the raw signal? How much of that is combining different images in an intelligent fashion? How much of it is applying intelligent filters? And how much of it is machine learning, right? So that's the whole pipelines which these different companies will build up. A lot of us would have seen things like night sight, or so modern day cameras, they can even take remarkably good photographs in night, right? When the light is not good. How do they do that? Again, they may take multiple photographs. Even when you seem to be moving your phone, they may be clicking multiple photographs, and then they'll have to stitch them together. And that needs to be very intelligently done. So that is a part of computer vision. But a lot of this is also now done using now machine learning algorithms. So specifically things like generative adversarial networks or GANs, and similarly things for motion, right? So if we want to capture a fast moving object, let's say we want to capture the moving of a car, right? How do you deblur that? How do you image stabilize that, right? So that's some of the things which Shanmuga and his group have done. For example, if you see this paper, fast motion deblurring using conditional generative adversarial networks. So again, I'm showing this as how I might approach these set of papers where I'm not working in these fields. But let's see an example. Let's just open this paper and see what we can get out of this in just 2-3 minutes. Right, so I may just read the abstract. There is a fast motion deblurring network, and it gives you structural similarity and visual appearance after deblurring an image. And it's using something like, so the benefits here is reduction in model size, faster than the closest competitors. Now, why do you think model size is important? Because many of the times these things have to be done on smartphones. You have limited memory. You have also limited compute. You don't want to be using all the compute, all your battery just to get one video processed, right? So it has to be fast. It has to be requiring lesser computation as well as memory, as well as qualitative and quantitative results. So it needs to be qualitatively looking better. Now, so this is now showing if a fast moving object is there and you take a blurred image, how can you sharpen that image, right? So again, you can completely do this in machine learning. You can think of this as signal processing plus machine learning problem, but that's the whole idea. And there are some very nice examples. You can look through this. And if we come back, so we can see another paper. It's called Depth-Wise Spatiotemporal Convolutional Neural Network for Human Action Recognition. So Shanmuga and group have also worked on things like, can we build a data set for yoga activity or similar activity detection? So many of these things have not yet been done specifically for activities which are more prominent in the Indian settings. So it's a very novel, very important contribution that way. And this is a paper which is now showing, let's just wait for it to load. So it's showing improvements over the standard vanilla convolutional neural network, employing techniques based on what you might have already studied earlier in your engineering degrees on things like Fourier transforms, right? So they end up creating some improved version of existing networks, which are not only faster, they require lesser memory, they're more accurate, and they've shown this for human action recognition. So for example, some of the things could be even activity recognition for the different yoga poses, right? Let's now move and talk about some of the work which Krishna Miyapuram and colleagues do. So he works on cognitive sciences or computational neurosciences. So think of the modernist scenario, especially during the COVID time. So all of us had very limited physical distractions. So all of us were mostly on smartphones, on devices, on our laptops, right? So we were perhaps not very mindful. We were not very well rested in some sense, right? We were all very distracted. So can you use some sensing devices? Let's say, can you look at the fMRI data or can you look at some EEG data? So think of putting a small sensor as a headgear and studying the brain activity. So can we put some of these sensors and get a sense of the brain activity during various phases of what you're doing, right? And then because it's very high dimensional data, it becomes very hard to interpret, right? Very hard to understand, to interpret, to learn anything out of it. So that's some of the work which Krishna and his group are doing. So for example, let's try and look at some of the papers. Again, I'll look at the Google Scholar. I'll reverse sort by the year. And for example, let's look at this paper, Nonlinear EEG Analysis of Mindfulness Training Using Interpretable Machine Learning, right? So mindfulness, think of it as it's an activity or it's a process you're following to try and focus your attention on limited or one object rather than it being distracted or wandering. You're trying to get it back. You're trying to look at the EEG data. So you're putting that headgear and you're trying to understand that what happens, which of the zones of the brain are activated when you're distracted, when you're not distracted, or can you tell the state of the person's mind by just looking at the EEG data? And if you can tell that, then what parts of the brain are important? How do they trigger? So you're trying to build some intuition as to why certain parts of the brain are important or which signal is important. So you may want to look at things like, right? So for example, these are some of the topographical plots. And maybe these are the different electrodes put, and maybe the colors as well as the circle width are telling you about the importance. So this is using something known as Shapley values, which is a game theoretic way of understanding the importance of certain features in predicting in the prediction task here, right? So there are some other similar papers which could be fairly interesting. For example, can you so using EEG dataset using naturalistic music listening comprising different genres. So for example, can you just looking at the EEG data, so just by putting at the sensor, can you understand what music is being heard or being played? Similarly, there have been some interesting work from the group. Can you tell about the different movies or what someone may have been seeing, right? So a lot of this has applications in healthcare. For example, you can see here risk prediction of Alzheimer's disease using deep learning of MRI scans, right? And there's another paper on early detection of Alzheimer's disease, right? So a lot of this has also very good backing in good health literature, motivated by that. Now let's come on what some of the work which I do, and then I'll finally go on to what Anirban does, because that's a little more theoretical in some sense. So if we look at some of the work which I do, let's just open this, one or two of the recent papers, right? So if you look at the first paper, it's called Spiromask, measuring lung function using consumer grade masks. So all of us are wearing masks. Can we use these masks and attach a very small sensor, let's say 50 rupees sensor? I can get your breathing data that way. And I can also ask you to do some maneuvers. Once you do that, can I collect that raw signal, apply some machine learning, and tell you about your lung health, right? So think of the way which Fitbit works or various smart bands work, right? But think of this as the same thing as the Apple Watch or the Fitbit, but for your lung health, right? Unfortunately, a lot of the very significant population in countries like India is losing lives due to poor lung health. A lot of this has also got to do with poor air quality, right? So it's important to be able to measure the lung function using something as convenient as a consumer grade mask. So if such masks are not available, these tests would cost you to go to a doctor, and the instrument might cost you 50,000, 1 lakh rupees. But now sitting at your home, you can do this measurement, right? Let's look at another paper which was done by the undergraduate students here. So can you generate some apparels using some text, right? So think of it as sometimes you have some idea in your mind, but it's very hard to convey that or to try to figure out what would be a good search query, right? Or try to figure out that clothes apparels, right? So maybe you want to say something like red and beige printed anarkali kurta, mandarin collar, 3/4 sleeves. And then this whole system will do some machine learning. So encode the text, use some GANs, look at similar images, and will create an output which looks like the following, right? And there are some other very good examples which we were able to create. For example, if you give these kinds of descriptions, long sleeve wash, cotton poplin shirt, you're getting something which is making sense, right? Relaxed fit versus, let's say, red kurta or yellow striped Nehru jacket. So you're able to generate these things. These will again help you to make such queries more easily, right? And more recently, we also had a paper on air quality inference. So air quality is hard to measure at all the places because the air quality monitors are few, but it's an important problem. So in this paper, we looked at a very flexible machine learning model called Gaussian processes. We were trying to estimate the air quality at places which don't have sensors, right? And we just show that we're able to beat the state of the art. Now, a common underlying theme in many of these papers you would have seen is the large scale of the data sets. The various challenges, some of them are coming from the Indian context. And you might have also seen that there is a limitation on the computational capability that generally exists. And that's where a lot of the work which Anirban and group come into the play. So for example, air travel would, for one passenger from New York to San Francisco, that may produce about 1984 pounds of CO2, right? Whereas if you're training a complex natural language processing model, so which are very common these days, by the way, so that is generating orders of magnitude more carbon dioxide, right? So these models are insanely complex. These machines run in data centers for days, just producing one run of these complicated algorithms, right? But do we need all of that? So this amount of energy could probably power whole cities for few days, right? And this unfortunately, the model's only getting more complicated. And at the same time, we are also trying to figure out solutions towards things like the reducing the emissions, right? So there's an important lesson to be learned here. And that lesson is that, do we actually need all the data, right? And if you're wondering about the big data problem, again, think of if you have to read through all the text in Wikipedia, right? There would be millions of pages, each would be thousands of words, etc. And if you have to build even a very simple trivial model, even something as simple as a binary classifier, right? Now you're dealing, or a simple linear regression, you're dealing with now high dimension data, you're dealing with large number of data points, right? But importantly, the data set may exhibit some properties which make it more amenable if you can use only a subset of the data or a smaller variation of the data. You don't need the entire data. So that's the question of, or that's the problem of core sets. Can I learn a model on a subset of the data or some subset of similar to the data, where the model, if I learn a model there, would give comparable performance, right? That's a huge win. You don't need to then train your models on these complicated machines for so many days, right? Now, this is a very theoretically important as well as very practically important problems, and there are so many interesting variants to it. For example, if you think about tensor factorization, so it may seem like a very complicated term, but think of the way which your Netflix systems would be, or your Amazon would be telling you which movie to watch, right? So these are generally solved using algorithms known as factorization, matrix or tensor factorization. And these are in the online setting. So each time you watch a movie, the Amazon or the Netflix systems gets a little bit more idea as to what movie to recommend you next. So think of this huge latent dimensional representation that they have of you, right? So you are maybe similar to some people around the world. You have watched these movies. Some other people like these movies, right? What genres do you like? What movies have what genres? So all of this information is encoded in some vector form. And this data is getting generated in the online setting. Each time you watch a movie or you put a like or a dislike on a certain movie, this is additional data being generated. For this huge sparse, because very few movies have been watched by very few people, can you still learn a core set, right? And can you also learn a core set for things like regularized optimization? So many of you might have heard about things like linear regression, but when you put some penalties on the weights of the linear regression, you get a regularization. So can you learn some subsets of data or core sets for such problems? Now, it's important that in many of these problems, you have to come up with certain theoretical guarantees, right? But there are other very important problems also. For example, fairness. So you want to predict whether a person should be getting a loan or not, right? That should not depend on the person's gender. That should not depend on the person's race, right? So these are very sensitive attributes. You'll want to build a model so these attributes don't end up deciding the decision for you, right? So this is the problem of fairness. Can you create a core set, a subset of or core set, which also is fair, right? So this is a very interesting and hard problem, right? And similarly, there are other implications. There are other similar papers. So this is towards reducing the data set. But then there is some work from Anirban group on reducing the models. So if we just open Google Scholar and just reverse sort by the year, let's maybe look at this paper. Gradient-free approach for pruning neural networks and initialization. So again, think of, you can reduce the time complexity or the time required to run these complex models by reducing the data. Secondly, you can also do so by reducing the model complexity. So that is what this is doing. It's saying that you have a huge neural network, you can probably throw away a lot of the information, a lot of the weights from the neural network, and you'll still get comparable result. So with that, I'll end this tour of the machine learning research in our group. Thank you.